Next speaker is Alán Aspuru-Guzik from Harvard University.
Hello, everybody. Can you listen to me well? Am I too loud? Okay. Well, thank you for the invitation to come here. It is really a pleasure to talk in front of this audience. I am a chemist that about 9 years ago switched from the chem pH to the quant pH world. And I work at the interface between chemistry and this field, and I'm very happy to talk here. So I had to modify my talk yesterday because of Twitter, so let's just begin with a Twitter story. Yesterday, John Preskill tweeted this tweet saying that there's a PRA article in quantum chemistry using quantum computer that is already out of date. There are big recent improvements. And this is the tweet about the article that is out of date. Then there is a tweet about the substantially improved quantum gate count reported here. This is by the same group. This is a fantastic collaboration between Matthias Troyer, David Poulan, Microsoft, that is really working really hard in quantum chemistry, and I'm excited to see their papers around. But even this tweet of John Preskill was outdated because there was a tweet a day before by David Meyer talking about our paper that has slightly better scaling than their paper. So in a sense, his tweet is also outdated, okay, by a day. Okay, so let's just come back to that story in a little while. Let me just begin by telling you quantum chemistry and how even tweets can be outdated right now in the last 6 months in quantum chemistry for quantum computing for quantum chemistry. So I'll be telling you about these first 4 topics here. Why quantum chemistry? Then I will go in telling you the gate model approach that Twitter is about right now. But I will also tell you about 2 other approaches that my group had developed last year and we've been working on that actually do not use gates to actually simulate chemistry. But let's just begin about the idea of quantum simulation and chemistry. Actually, I'm going to allude to one of the last slides of Jake, right? What physics or chemistry can we learn if we were to have a quantum simulator? I've been arguing, and I continue to argue, I think, that if you want to make a quantum simulator, it has to be beneficial to society. And I am a fan of phase transitions as well, but I think if we understand some of these phase transitions in physics, we might not really help us, solve problems like the energy crisis or something like that, right? So why would we like to do quantum chemistry? You might argue we have very nice computers, and certainly so. I mean, classical computers grow in power as you increase the size of the basketball court-sized rooms where they actually reside, and you have more and more processors. And the approximate methods, such as coupled cluster, that scales as n to the 7, this scaling of the approximate methods is important because now in the scaling of the exact methods, we're arguing about exponents. Chemists don't like coupled cluster because it really cannot treat many atoms because it scales as n to the 7, n to the 5, n squared, even n. Okay, so you have these scalings, polynomial scalings translate eventually into the number of atoms that you can treat with different approximations. The gold standard, roughly, this perturbation theory method, well, it takes you to the order of 100 atoms. But, really, the exact simulation in classical computers doesn't scale very well, and we won't get to 10 atoms, maybe in a very long time, okay? And the issue, of course, if you use approximate methods, which, I mean, in my group also, part of my group, as I'll show you in the next couple slides, uses them to actually try to do something, beneficial to society. You have to be very careful about all the errors that come in the traditional methods that we all use, say, for molecular screening, like the so-called density functional theory. The full configuration interaction, in physics also known as exact diagonalization, is the exact target that we want to use quantum simulators to get to. Okay, and that one, of course, will change the way we do quantum chemistry because rather than having an explanatory tool or sometimes a screening tool that has a big error, we will move into the domain of having a predictive tool, right? The simulation will tell you what's happening, period, right? So we will be able to much more quickly design materials. So even this simple picture, I mean, I really love this picture by this paper by Gross and coworkers. When they scan a tip and they actually see the wave function of this pentacene. Pentacene, of course, for you physicists, is just a piece of graphene, okay? But what is really nice about pentacene is that it's really hard to study the electronic structure of pentacene, even harder when it's on a surface. It leads to strong correlation. Garnet Chan at Princeton has studied very carefully with DMRG the electronic structure of the system. So even the system is extremely challenging for quantum chemistry, right? But if we are able to do that, then we're able to simulate the nanoscale and maybe simulate the coupling of the plasmons to the MV center impurities that Jake Taylor was telling you about, right? It would be nice to have a simulator that simulates itself, right? Another interesting thing about it is that 30% of the DOE supercomputer time is used for chemistry applications. So that's a good prediction that if we were to have a quantum simulator for chemistry, most likely will be very utilized to replace this 30% of supercomputer time and do something useful. I'll tell you an example of something useful that we did about, well, I guess 3 years ago already. We used the computer to design this organic semiconductor here, okay, which actually was at the time the second highest Hall mobility material. This has a mobility that is about 10 times larger than amorphous silicon, but it's a plastic. Now, of course, our stuff is outdated. You know, as all fields, this thing actually in 3 years is already a mobility is a factor of 10 of this, roughly, okay, coming out from our collaborators and other people in the organic electronics world. So maybe one day we'll have an organic electronics simulator. I'm looking at Jake. Okay, so what can you do if you actually use screening carefully? So that's one of the big research areas of my group. This is probably my paper in which actually we have done something more useful for humanity. We actually took a classical simulation, screened about 10,000 molecules, very close to rhubarb molecules, actually, it turns out. Quinones, they're called, to actually store energy. Okay? There's very simple molecules here. And that's the cheapest battery that we know of. Okay? So if you want to store solar energy for your, for a renewable energy future, probably you will be using something like our quinones, we believe. It replaces metals in batteries. And this is my only picture as an experimentalist here with our quinones storing energy. Okay? But what am I telling you all this story? Really to motivate why quantum chemistry. Many people are asking, what is the use for a quantum simulator? I want to use this audience to try to convince you that quantum chemistry is probably one of the first applications that you want to implement in a simulator, because then you will be able to simulate these quinones exactly and not do experimental fitting like we did and so on. So now that's about motivation. So let's talk about how to do it on a quantum computer or a quantum simulator. So let me just introduce some terminology here. Say you take the acetone or any molecule you want, and usually where you want to start with is with a self-consistent solution of its wave function in a local basis. We'll come back to locality strongly in this talk. And that will lead to what we like to call molecular orbitals, which are just the single particle eigenstates of this molecule, and so-called integrals, or basically a way of writing the second quantized Hamiltonian as a function of integrals based on these orbitals. And you have first, one electron terms that actually are just hopping between these different orbitals due to one electron kinetic energy and potential energy. And then these two electron scattering events, right? And this gives you a Hamiltonian that has, n squared terms for this one electron terms, and then n to the 4 terms for these two electron terms, okay? So back when I was a postdoc in 2004 and 2005, I was thinking about how to use simple algorithms such as set-Lloyd's phase estimation and so on to actually simulate quantum chemistry using this molecular Hamiltonian. Just to remind you, what goes on is that these parameters are obtained efficiently these integrals are obtained efficiently with a classical computer, okay? And those are the parameters for the Hamiltonian that you're going to simulate. I want to make a difference between the simulations that usually you hear about, which are lattices or periodic systems, where all these so-called integrals, right, will be very similar, right? They will be hopping terms, or there will be side energy terms, and so on, that are all very similar amongst all your different sites or qubits or atoms in your lattice, etc. For doing chemistry, you really want to have very, very fine control over these side energies and couplings, or whatever you want to think about them, right? Extremely fine control, because after all, you are after a very fine chemical energy difference, okay? So this is a slightly different approach to quantum simulation in the sense that you need a lot of control, again, because you're not after, coarse phenomena, but you're after really, really precise numbers, okay? So this is the single electron integrals, as we call them, and two electron integrals, again, classical parameters that come into designing the Hamiltonian. So each molecule is just an instance of this many-body fermion Hamiltonian, right? So, okay, so how do you do it? Okay, the Twitter of John Preskill and a lot of the approaches that we worked on as well at the beginning, now we are moving on beyond them, still working on them a little bit, is using time evolution, right? You take this molecular Hamiltonian, and then you basically time evolve it in small salami slices, as I guess Andrew White will be telling you more about, okay? And then you need to transform the Hamiltonian from fermions to spins, And one way of doing that, to distinguishable spin 1/2 particles, and one way to do that is to use the Jordan-Wigner transformation. Peter Loeb, my collaborator, proposed the use of the Brabby-Key type transformation actually as a way of reducing this extra order of scaling that you get from this transformation to a logarithmic overhead. And that's very important for what I'm telling you later. Okay, so there's a lot of progress based in the last 9 years over this quantum chemistry and for quantum computing. And again, just to remind you how the readout in these time evolution methods goes, you entangle a time register with the time evolution of the system. Successive powers of the time evolution operator will basically represent binary digits in an expansion of the energy of the system that is actually mounted as a phase in this state that is therefore read with a quantum Fourier transform going from the time domain to the frequency domain. You get a little readout signal there in your quantum circuit that will be proportional to the molecular energy. Okay, so that's basically the approach that Seth Lloyd and Abrams proposed quite a bit ago. And again, this is what I did first in 2005, and then we worked out the full quantum circuit in 2011. This was the first project for my first graduate student, and it took a while because he did many projects in between. And then in collaboration with Cody Jones and the Yamamoto group, we did an error correction analysis of it. So this will give you more or less the idea of the sketch of kind of like the order 0 algorithm. What is really nice, of course, is the size of the system that you can simulate scales linearly with the number of qubits. 2 qubits give you 1 basis function. About 30 basis functions per atom gives you what is called chemical accuracy, which means 1 kcal per mole of error in bond dissociation energies. Okay, so molecules that I like here, benzene, caffeine, cholesterol, I like to eat a lot of meat, I guess, can be simulated with order of hundreds of thousands of qubits, okay, logical qubits. When you actually go ahead and propose error correction, and again, this is primarily the work of Cody, and we just provided parameters and helped him figure out this calculation. When you actually translate this to error correction, then lithium hydride, which is a molecule that we can simulate right now in a classical computer, what seems to be like a good benchmark, will require about 100 physical qubits and around 10 to the 7 gates to be realized. Okay? I think that's a good example of what would you need if you just do these time evolution methods. Even back then in 2011, we pointed out something that was pointed out recently by Microsoft and in much more detail, and is the idea that, of course, it really is prohibitive to do. Lithium hydride is fine, but if you actually go to cholesterol, again, this molecule very close to my heart, you actually have the problem that you have 10 to the 15 2-qubit operations, okay, and this is a single trotter time step. So, around that time we got depressed and we started designing these 2 other methods I'll be telling you about, okay? But nevertheless, then I'll tell you more about it, but I'm gonna make an interlude. Andrew White is gonna tell you more about this in his next talk. And if I'm talking fast, he will talk quadratically faster, okay? So the hydrogen molecule was done in collaboration with Andrew. It started as a phone call between Queensland and Harvard. It was a very fun, one of my favorite papers. I'll show you a couple plots of it. Then 4 years later with Jeremy O'Brien at Bristol, we did the helium hydride plus ion. It's from a 2x2 Hamiltonian, which is the most expensive way you can diagonalize it here, to a 4x4 Hamiltonian. And I'm not going to have time to tell you, but we have an algorithm also in quantum optics we like to call cooling like a demon, just appeared in Nature Photonics, that allows you to prepare states. So this is some of the things that we've done in quantum optics related to this, and there's a review here. So just to remind you how it looks like, Andrew will tell you much more about it, but this is a macroscopic device that he used to simulate the hydrogen molecule. Turns out for doing hydrogen, you can do many tricks that you cannot do so far. We're working out how to use them now to actually produce. These are real numbers from his quantum simulator / quantum computer, optical. Okay, there's no errors there because it's digital. It has error correction. You can do that for these 2 qubits, and the error correction is just majority voting. And here you get the eigenstates of the molecule as a function of separation. Again, it's really a 2x2 system, but you can show that with quantum optics you can actually get this. Okay, so that was a kind of the base level experiment. And now let's come back to Twitter, right? Let's come back to the story. So what happened is that there was a very nice paper where slightly pessimistic too, and this is a story from from Microsoft, Dave Wecker, Matthias Troyer, Matt Hastings, okay, which was covered in August 6th, just published in August 6th and covered, I guess, yesterday or 2 days ago into the physics aps.org website. And they basically, it says the gate count goes by a factor of 1 billion when you use larger molecules. And therefore, this will be very intractable using quantum computers. So if this was the case, then maybe I would have changed my topic and told you about one of my other research areas, right? But turns out that, I mean, when this paper came out, we just pointed out that their estimate was extremely pessimistic, okay? It's a good upper bound, but it's very pessimistic in many ways. And one of the reasons is because they use random molecular integrals, okay, to actually make this numerical study. And so therefore, they had a scaling where m is the size of the molecule, right, of n to the 11. So you see, now we're talking about polynomial scalings. Even back then, Peter Love, my friend, likes to say, come on, guys, we went from an exponential scaling to polynomial scaling, and now people are angry that the polynomial scaling is 11. Okay, yes, it sucks to be 11, right? But it was polynomial still remember, it's an exponential improvement. Well, 11, that was in December 2013 when that came out in the archive. Then the Microsoft guys got to work, and they kind of set up their own strawman, and they killed it because then a few months later in March, they went down from n to the 9 to n to the 7, and they started saying how great they were because they went from n to the 11 to n to the 7, which is fun. I mean, those papers are fantastic. We're reading them and studying them and using them. And then their latest paper that appeared in June has a scaling that they numerically estimate to be between 5.5 and 6.5. So using some techniques that they used and using some of our chemical knowledge on locality, which I'll tell you, we have a very, very simple way of estimating that for molecules of a decent size, using the Brabbe-Kitaev estimation and estimating Trotter errors and similar studies like this, that's a paper that was tweeted 1 day before John Preskill realized it. We find a better scaling, which, at least by a factor of 1/2, n to the 5 log m scaling for simple molecules. What is nice about that one is that we make non-numerical studies really, other than the quantum chemistry simulation, and we make upper bound estimates for everything else, okay? So this is actually, again, an upper bound. And the other cool thing is that these things that they did here can be combined with our locality arguments to further reduce this. So Andrew White this morning was telling me that if this continues, maybe by the next ICAP, it will take 1 gate to simulate a molecule, right? Let's see, okay? So what does locality for orbitals matter? Chemists usually think in the molecular orbital basis. We are physicists, chemists, and we all think about eigenstates, so why don't we just do the numerics on the eigenstate basis? Well, because for this carotene, a molecular orbital in the carotene might interact very well with a non-molecular orbital, right? Therefore, that leads to long-range interactions, that leads to many more terms in the Hamiltonian. But chemists have been trying to do linear scaling for a long time. In the first slide of this talk, I show you linear scaling method. So if you go back to those linear scaling quantum chemistry methods from the 90s and the 80s, you find out, well, you can do something called orthogonalized atomical orbitals. You take your atomic orbitals, orthogonalize them, and now you have a basis where this guy doesn't talk to this guy, right? So let's just build the quantum chemistry Hamiltonian in that basis and analyze the scaling, and that's what we did. So if you take a look at, for example, how these two oxygen and nitrogen atoms will interact with each other, and we use what is called a Gaussian basis, the preferred basis in chemistry, you can calculate the Gaussian overlap integrals very simply because of the Gaussian product rule. And you notice that, basically they decay exponentially. And then you get the fact that the 1 electron integrals that survive, okay, remember we had n squared of them, they go back to n, okay? And we'll show you numerics about what is the size of the molecule, but roughly about half of the carotene I show you, okay? And the same thing here, the M4 terms in reality are m squared, okay? Again, if you go back to the work of our Microsoft colleagues, there's a lot of things you can do still beyond that. You can think about which terms do not commute with each other, do adaptive Trotter time steps, do a lot of tricks that will even improve this, reorder your gates, sequences, etc., which is what they've been doing. But even if you just do this, you just say, look, I know as a quantum chemist that if I truncate, to a certain number of terms, and we know that a lot from numerical experience, really your numerical answer, we won't change beyond chemical precision, right? So for the purpose of chemical simulation, this is exact, right? We don't care what happens after chemical precision, okay? So therefore, you just look at the orthogonalized atomic orbitals, and then you screen them, okay, with different parameters. What I want you to look at, there's too many things to look at, but you see how when you screen or do a cutoff, okay, based on a slightly larger number of the integrals between the molecular orbital in green and the screen molecular orbital in blue, you really don't get too much improvement. When the orthogonalized atomic orbitals, you really get this change in the scaling, okay, at a very reasonable size, okay, about 20 hydrogens, okay. This is a chain of hydrogens separated by 1 angstrom, okay. So now I have very little time, so let me just take you to what I like to call the hitchhiker guides to chemistry simulation. There are many ways of skinning a cat, and the most important thing I want to tell you, okay, I just realized I just got a time warning, so I'm going to speed up a little bit, is that you don't need to do time evolution really if you're after energies, okay? So all this time evolution discussion we're having, you can avoid in some sense if you do this. This is the map of all the approximations that you can do, okay? You start with a full configuration interaction Hamiltonian. Oh, what did I do? Okay, and what I told you about is that we do a Born-Oppenheimer approximation, we do second quantizations, compute the integrals, Jordan-Wigner or Brabby-Key type transformations, trotterization, and you do phase estimation. So this is what we've been working on, that Microsoft has been working on. But what if you actually do something more straightforward? When you use a classical computer to actually do quantum simulation, you really don't trotterize and time evolve like that. What you do is you calculate an expectation value and variationally optimize the parameters. We argue this is something very, very straightforward that you can do with a quantum device. Any quantum device that you have in your fridge or in your room temperature, as Jake was emphasizing, whatever quantum device you have, in reality, prepares quantum states and measures them. And that's the only thing you need to actually do simulation. Okay, so what we do is we say, let's just go and do and not do the Born-Oppenheimer approximation, and directly, we're going to pay a price, but directly go and do variational optimization. Okay? So what you do then is assume that the hardware that prepares the quantum states is the actual theoretical ansatz for your wave function. In other words, the entanglement power, the state preparation power of your device is what is going to give you the wave function that you're actually going to be simulating. So you guess a wave function based on a polynomial number of parameters, and of course the ansatz that you have to use has to be powerful enough. Prepare it in the system and evaluate its energy. What you mean by that? You interpret the measurements of the expectation values of the wave function as a Hamiltonian you design. And then vary the norms polynomially and repeat, okay? And so in other words, a quantum computer can calculate expectation values of single qubit and many qubits very easily. You prepare and measure, prepare and measure, prepare and measure ad nauseum, okay? But I don't want to do in the quantum computer addition, averaging, optimization. I don't want to do all that stuff. All that stuff I do in the classical computer, okay? So in other words, what we do is we say, well, you can write any kind of these many-body Hamiltonians as a function of spin operators. After all, that's what we do. We transform to qubits, and then we look at those qubits and calculate expectation values of them. The integral, so to speak, that I was telling you about will be turned out into these terms here that are prefactors to what you measure in the device, okay? So in other words, well, if you want to measure the energy, measure each one of the terms in the Hamiltonian and sum them up. Okay, there's an overhead, of course, to the precision that you need to do that, but we have worked that out as well. And then, so for a quantum computer, you do, again, expectation value measurements. In the classical computer, you add, multiply, calculate, calculate the total energy, for example, or any property you want. And now you do what you do in classical computers. You minimize expectation value of the wave function of the system. So this is very simple, but nobody had done it before. And to me, it's a very simple approach to quantum simulation. You can parallelize if so you want. You can have, as my student Jared likes to say, many quantum processing units, okay? Or many quantum devices that actually can simulate different terms of the Hamiltonian. You add them in a classical ladder, and you optimize, okay? And this paper just appeared in Nature Communications that shows you how to do that. This is another collaboration with experiment with quantum optics with a group of Jeremy O'Brien. I'll show it to you in a second. So, but again, the whole idea is that now we really actually don't even care too much about what's going inside of the quantum device. We're actually abstracting it into a black box, okay, that has certain number of knobs that we variationally tune to obtain an expectation value, okay? So this is the next level technology. I guess that was a macroscopic optical table. Now we're going into waveguides. It has a lot of noise because of this, kind of coupling that you see there. But it's nevertheless, it's a tunable optical device that actually gave us now a 4x4 matrix. So for all of you that criticized me for my 2x2 matrices, now we're by 4x4, okay? So wait another 4 years. So really, I really ran out of time sooner than I expected, but I'm gonna tell you in the last 1 minute, okay, one more thing. So this thing has advantages because the only thing you do is prepare and measure. The scaling is n to the 6, so oh my God, we're a little bit worse than our other method. but it's actually pretty awesome scaling too. That factor of 2 comes from the averaging of all these Hamiltonian terms and so on. But let me just continue and show you one last thing. What you need to do also, potentially, is to use what adiabatic methods are using, these adiabatic machines like D-Web and so on. But now you want to make them universal. You want to use a final Hamiltonian that has many body interactions. And we just proposed how to do that. It took us a while, but the most important thing was to understand how to make these gadgets properly, so to speak, these perturbative many-body gadgets, and the fact that we needed to use the Brabby-Kit-Taube transformation. But because I ran out of time, I'm going to just show you. My computer just crashed, which is, you see, she said, you know, your computer has to crash, stop. Okay, the last thing that I flashed to you, and then maybe I can run it again, okay? PowerPoint has failed. I need a quantum computer. Oh my God. I hate PowerPoint. Okay, so the last plot I'll show you then is basically how would an adiabatic device look like, okay, if you were to do this. Okay, so you transform the many-body Hamiltonian to a many-body adiabatic Hamiltonian. You will end up with this little, this is a hydrogen, by the way. It's about 20 superconducting qubits. Now you need different couplers, right? You just cannot use just the ZZ couplers that D-Web has. You need to build new couplers. But if you build those new couplers, this machine will be fully quantum, will be simulating adiabatically the ground state of quantum chemistry, and will also have very nice scaling. It has problems with the size of the couplings that you need to put in, but that's okay. We'll work them out, or Microsoft will work them out. So you show the picture of my students, please, computer, okay? This is me, this is Peter Love, this is Jared, and this is Ryan. And if I have any time for questions, I'll be happy to answer them. Thank you.
We have time for a couple questions. Anyone? Okay. And while we're making the mic down there, it's not my fault the computer crashed, I promise.
Maybe you had telepathy. You were showing me the 1 minute remaining and then my computer crashes. So maybe you told the guy to do something or something.
Maybe it's a quantum computer and something.
Yeah, quantum teleportation, yeah. Okay.
For the variational methods, does this give you excited states as well as the ground state?
Yes, you can do some a method called folding. You can subtract the term from the Hamiltonian and square it. So you add more terms to your Hamiltonian, but that's a classical numerical technique to get excited states. So just basically do h minus lambda square. You move the lambda, you get excited states.
All right, thank you. More questions?
I have this one here.
Yes.
Yes. Maybe I missed it, but on which basis can you claim a quantum speedup in your...
In which basis? In all bases. I mean, quantum speedup on the quantum chemistry, you mean?
Yes.
Quantum chemistry Hamiltonian, even in the most pessimistic estimates that just appeared earlier in 2013, has an exponential speedup over a classical computer because the trotterization and the phase estimation algorithm will give you a polynomial algorithm. That's well known, really. So in any basis, local, non-local, etc.
By basis, I mean what is the argument for claiming a speedup is that your scaling is polynomial. This is the main claim.
Yeah.
Yeah. Okay.
It can happen, I would say, in any decent basis. You want to express real space cubes. You can express it in Gaussians. You can express it in plane waves, etc.
And also, if you want to implement it, you want to use linear quantum computing, basically.
We have worked on proposals for many types. For example, with Enrique Solano, we worked out recently a proposal to do it with ion traps.
Linear quantum computing will sort of kill your polynomial scaling.
Andrew White will tell you about that in a second. But we have worked out ways of doing it with superconductors, ion traps. We're agnostic to that. We designed the algorithm. We work with experimental colleagues. Let's see which platform. We just heard maybe microwaves, cavities will be the thing that will be implemented. Who knows what's going to be finally implementing this? Okay.
Right, one more quick question.
So density functional theory, which is the standard method used in theoretical chemistry, is, I'm here,
Okay, sorry. It's a big
So,
audience.
and we know that these traditional, let's say, methods of quantum chemistry work very well because we look around in the world and we know that they work, okay? So where are the places in which I really need to calculate quantum correlations to such accuracy that it really will play a role for surrounding world?
I mean,
This is my
look,
question.
they work. I just got this paper to design this molecule, so I use them all the time. I know very well how they work. They have errors about a few kcals per mole, okay, in the properties, okay. For doing those predictions, I had to fit to experiment, okay. I don't want to fit to experiment. I want to predict the number exactly, okay. So a lot of the quantum chemistry, when you actually use it for predicting the property of a material, okay, like redox properties or like absorption energies, etc., you need to fit to experiment, correct gaps and stuff like that. You avoid all of that. You get an exact prediction. So it's true that density function theory is extremely powerful, but you completely obviate it if you have a quantum computer. You won't have errors, right, except the numerical error of the simulation. So it's going to be powerful. Yeah.
All right, let's thank Alan again.
Okay.